Okay, so this is the last talk of our session. Will be presented by Manuel Dominguez de la Iglesia from UNAM in Mexico City. And you can see the title there is Stochastic Factorizations of Berkeley chains and Darboux transformations. Thank you, Manuel. You can go ahead.
Thank you, Luis, and thank you to the organizers, to Jean-Philippe and Diego. And thank you all the people that remained to the last talk, although it's a little bit late in some places, but I promise I will try to make it shorter than 45 minutes, but we will see. Well, this is a joint work with Alberto Grünbaum and my student, Claudia Juarez. We have been working on this for the last 3 or 4 years. And well, and also there are some work in progress. So I will try to explain or give a summary of all the results that have been published in the last or 3 or 4 publications in the last 3 or 4 years. So we start with what is the main idea of this talk. So we will work with a birth-death chain or discrete-time birth-death chain, which is irreducible, and we will be focusing on the states, different state spaces on the integers, and we will study or will show the 3 cases. No, one with finite number of states, then the non-negative integers, and also the last case, a more interesting case of the whole set of integers. So this kind of processes, of stochastic processes, are characterized by the one-step transition probability matrix, which in this case is a tridiagonal matrix, or in the context of orthogonal polynomials, what is called a Jacobi matrix. So the goal will be to find, or to try to find, stochastic factorizations of this matrix P, these tridiagonal matrices, in principle in 2 factors, no? And we want to each of these factors to be an stochastic matrix itself. So the natural choice for these factors would be upper or lower bidiagonal matrices, what is called the LU or the UL factorization. But we will see that, for instance, in the case of a state space, the whole set of integers, then we can consider different factorizations, not only LU or LU factorization, UL factorization. So the main motivation for looking for this stochastic factorization is to divide the probabilistic model for the original matrix P into probably 2 simpler probabilistic models corresponding to the matrices P1 and P2. If we are able to find simpler probabilistic models, then the model for the matrix P will be just a combination of the one experiment corresponding to P1 and one experiment corresponding to P2. So this is basically the main motivation of this stochastic factorization. So in this talk, we will try to answer two questions. No? First of all, under what conditions we can guarantee the stochastic factorization, which in principle, we don't know when it's going to be possible. And we will see that not all birth-death chains can be factorized into stochastic matrices. And the second question is, what happens, what is called with the discrete Darboux transformations, which has been mentioned in previous talks, that is just the reversing the ordering of the factors and see what happened with the new process. So if we have the spectral measure or matrix, depending of the state space of the original process or birth-death chain, what is going to be the spectral measure associated to the discrete Darboux transformation? So this is basically the 2 questions. So we will divide the talk in 3 parts. First, we will focus what happens in the finite number of states, then the non-negative integers, and then finally the most interesting case of the whole set of integers. So we start with the finite number of states. So this is what we're trying to do. We start with a tridiagonal matrix over here, and we look for, we will start with the UL factorization. The matrix PU will be upper diagonal, and the matrix PL will be lower diagonal. And we want everything, all these matrices to be stochastic, meaning that all entries has to be probabilities, and the sum of each row has to be equal to 1. So, and direct identification of the coefficients gives the following relations between the original the probabilities and the new probabilities R, S, Y, and X. So since we want everything to be stochastic, in principle, we see that this yn here has to be equal to 1, and s1 here has to be equal to 1. So this will give you conditions, and here the only relevant relations will be the first one and the third one, because this one, using the property that they are stochastic, is trivial. So let us focus in these two relations, and let us do some computations to see what is happening here. So these two relations, the first one is an equal xn sn plus 1. This is what we call the first relation. The index n goes from n1 to n minus 1. And the second relation, we will call this the first one. And the third relation, sorry, is Cn equals to yn times Rn from n equal to n to the final n. We will call these two relations. So how to compute all the coefficients xn, yn, rn, and sn? So we start with y0, that is going to be a fix. The condition of the stochastic matrix of PU gives you x0, that is 1 minus x0, y0. And then we're using here the property 1, and see that s1 has to be equal to a0 divided by x0, but x0 we computed before. And because PL has to be stochastic, then R1 has to be 1 minus S1. Okay, this gives you the first set of relation. So now we use the second relation to compute the value of y1. Y1 is going to be C1 divided by R1, but R1 we already had before. And from here, using again the same stochastic property, x1 is 1 minus y1. And again, using the relation 1, we have that s2 is equal to a1 divided by x0, x1, sorry, by x1 here, x1. And finally, R2 is going to be 1 minus s2. Right. So if we write S2, we see that is A1 divided by X1, but X1 here is 1 minus Y1, but Y1 is C1 divided by R1. R1 is 1 minus S1, but S1 is A0 divided by X0, and we get this relation, okay? So here we see that this structure is familiar with the and it's going to be or some kind of truncated continuous fraction. So we can do this until the end, and we have that EYM minus 1 using the second property. Then it's going to be Cn minus 1 divided by Rn minus 1. Xn minus 1 is going to be 1 minus Yn minus 1. Then using relation 1, we will have Sn equal to An minus 1 divided by Xn minus 1. And finally, Rn, the final one is 1 minus Ssn. That if we look at the relation, this has to be exactly the coefficient Cn, okay? So we can write this final relation in the following way. Then we can write Cn, if we again write 1 minus Sn, but Sn is An minus 1 divided by Xn minus 1, and so on. So then we will see that we will find something like this: A minus 2, 1 minus Cn minus 2, and so on, until the last one, which is A0 divided by Y0. Okay. So this is the main idea of how to compute the coefficients so that the two factors are stochastic. Okay. So since in this case the steady space is finite, then from this last two relation we can compute the first parameter Y0, and Y0 is not a free parameter anymore. So from here we can write that the parameter Y0 is exactly 1 minus A0 divided by 1 minus C1 divided by 1 minus A1, and so on, 1 minus C2 until the last one, which is an minus 1, 1 minus Cn. Okay, but from here we see that this parameter Y0 is going to have some kind of continued fraction structure, which will be extended to the general or the infinite cases. Okay, so in this case, this is then the factorization will be unique, but we are considering here the situation where all these coefficients are Sn, Rn, Yn, and Xn has to be probabilities. So there is a very old result by Whitehurst from the 60s, more or less, that gives you that under the condition that we want to have the stochastic factorization, if we Xn and Yn, if these are probabilities, then we have that the spectrum of the eigenvalues of the transition probability matrix has to be inside the interval 0, 1. Okay, so as long as the eigenvalues are positive, then we will have that the stochastic factorization will be possible. Okay, so then we will see a couple of examples. For example, this example of the symmetric random walk with constant transition probability. This is an example where we cannot do this stochastic factorization, because in this case the eigenvalues are not inside the interval 0, 1. So it's not possible to perform this stochastic factorization. But nevertheless, in this case, this matrix, it's possible to see that the eigenvalues are all positive. And in this case, we have the stochastic factorization, the UL stochastic factorization. This is PU and this is PL, and the situation is unique. Okay. In this case, the Darboux transformation, that's reversing the order of multiplication. We have that the Darboux transformation, this given by P tilde, is going to have the same eigenvalues as the original matrix, and the only thing that changes are the corresponding eigenvectors. Okay, but that's the situation here. As for the LU factorization, we do some similar analysis. Yes, now the relations are a little bit different, but in order to compute the coefficients, we do exactly the same thing as before. But in this case, the parameter Y0 is not, or we don't have to compute it later, because here everything has to be, well, for example, from here we can compute X0 equal to A0, then Y0 from here, and from the third relation we find the rest of coefficients, no? Y1, or in this case R1 equal 1, 0, 1, 1, and so on. Okay, so basically it's the same approach as I wrote it before. Okay. Now, in this case, this LU stochastic factorization will always be possible as long as the eigenvalues of the matrix P are contained again in the interval 0, 1. Okay, and similar things happen with the Darboux transformation. Okay. So with these ideas of how to build these stochastic coefficients, no, for this stochastic factorization, then we will explain what happened in the case of the infinite number of states. No? So we will focus now in the non-negative integers. In the case of non-negative integers, now the matrix P is a Jacobi matrix, is an infinite Jacobi matrix, and we ask for the same question. No? Under work conditions, we can find a stochastic factorization, no? With PU and PL stochastic matrices. Now, the problem is that in principle, the eigenvalues of P can be an absolutely continuous measure. No? So here we have to apply the very well-known spectral theorem to find the corresponding spectral measure associated to P. And in principle, this is not so easy as in the case of finite number of states, okay? But nevertheless, we have the same relations as before, the same way of computing the coefficients xn, yn, rn, and as n. But now in this case, the parameter y0 will not be explicitly computed, and we will have a free parameter corresponding to this UL factorization, okay? In the case of LU factorization, now there will be no free parameter. That's the difference between the UL and LU factorizations in this situation. So under what conditions we have this stochastic factorization, then we will have to consider this continued fraction, as we explained before, where the coefficients are, we have to change A0, C1, A1, C1, and so on in this structure. And in order to have a condition for stochastic factorization is we need somehow that this continuous fraction is convergent and the value is between 0 and 1. Okay, otherwise it will not be possible the stochastic factorization. So here is the main theorem. One way of ensuring the convergence of the continued fraction is assuming that the convergence, this convergence satisfies the condition in such a way that the continued fraction is always between 0 and 1 and is convergent. Okay. So in that case, in this case, the UL factorization is stochastic factorization will be possible if the free parameter y0 is chosen between 0 and the value of that exactly that continued fraction. Okay. As for the LU factorization, we will have it is going to be possible as long as this continued fraction is converging and it's between 0 and 1. Okay. And finally, we have this condition that since we're assuming that the continued fraction is between 0 and 1, we can apply the same result by Whitehurst, and we can say that in order to have this stochastic factorization, then the support of the spectral matrix has to be the spectral measure has to be inside the interval 0, 1. Okay. Well, the Darboux transformation of these two cases, the UL and LU case, are also very well-known results. In the case of the UL case, we have that if psi is the spectral measure associated with P, and consider the discrete Darboux transformation, this P tilde, and try to find the psi tilde associated with this the spectral measure associated to P tilde. Then if we have to assume that the -1 moment is finite, is well defined, and this Darboux, the Darboux transformation measure will be the following expression, will be what is called a Hieronymus transformation, which is basically divided by x the spectral measure and added some Dirac delta at 0, at the point 0. And here the magnitude of this Dirac delta is written in terms of the free parameter y0 and the -1 moment, okay? So this will be a family of spectral measures in this situation. This is also a very well-known result, and the result for the LU case is also it's not similar, but in this case the corresponding spectral measure associated with the Darboux transformation is called what is called a Christoffel transformation of the original measure, that is just basically multiplying by polynomial x. Okay. Okay, these are very well known results. I will give you now brief example of the Jacobi polynomials supported on the interval 0, 1, so that the stochastic factorization will be possible. We normalize the polynomials in such a way that at 1, the value of 1 is equal to 1, okay? In that case, the free term recurrent relation is the following, with the following coefficients, and these coefficients, it's easy to see that these coefficients are all probabilities, and the Jacobi matrix is a stochastic matrix. In this case, there are two free parameters, alpha and beta, with the usual restriction. So in this case, if we call alpha n the sequence of alternating coefficients, A0, C1, A1, C2, it is possible to see that this sequence is a chain sequence, no? Meaning that we have this representation, and we have M0 has to be between 0 and 1, and for the even indices we have this expression, and for the odd indices we have that. So we have a chain sequence. So that means that we can compute explicitly the value of the continued function h, okay? For example, in the book of Shihara, you can find that this continued fraction is given by this value, 1 minus L, the inverse of 1 plus L, where L is the following or the following series, that in this case is possible to sum, and the value exactly of L is going to be beta plus 1 over alpha, okay? So we use this theorem, and our main theorem says that we can have the stochastic UL factorization as long as the free parameter y0 is between 0 and this 1 plus L minus 1, okay, which in this case is this value. So for that we need that the parameter alpha has to be positive. Beta can be greater than -1. So then, for every value of the parameter y0 in this range, we can find this stochastic LU factorization, okay? And in this case, since the continued fraction h is between 0 and 1 and it's convergent, then the stochastic LU factorization will be always possible, okay? And the Darboux transformation, since we have an explicit expression of the Jacobi weight, so we can compute the -1 moment, which, as before, is well defined as long as alpha is positive. Here is the Darboux transformation, the Hieronymus transformation in this situation for the UL case, and the same for the LU decomposition. We have a Christoffel transformation, which is just a shifted number. We have to shift alpha and change it by alpha plus 1. Okay. So this is an example where we can do everything. And in one of the works with Alberto, we also use this stochastic factorization to find an easy model for the Jacobi polynomials, so in terms of Urm models. Okay, so let's go to the final part of the talk. This starting what is happening with the steady space, the whole set of integers. Okay. Well, in this situation, everything changes because the transition probability is doubly infinite stochastic matrix. Okay. So things get a little bit more complicated, but we ask the same question, no? Under what conditions we can perform the UL or LU stochastic factorization, and the same as before, we have the same relation between the coefficients and the same way to compute the coefficients. Okay. So now the new thing about when it's going to be possible the stochastic factorization is that we have to introduce a new continued fraction which considers the negative values of the indexes. Okay, we have h as before, but now because we have a doubly infinite matrix, we have to consider the negative indexes. So now we have to assume that both continued fractions are convergent and h prime has to be less than or equal to h in order to have the same theory. Okay. So in this case, the theorem in the case of the UL factorization, we have again a free parameter y0. But now, in order to have the stochastic factorization, this y0 has to be bounded from below by this continuous fraction h prime. Okay. And the new thing about the LU case, different from the previous situation, is that now we will have again a free parameter, okay? And this free parameter we will call R0, and this R0 has to be also some conditions on this between H prime and H, okay? So this is the new thing about this situation, that in the case of LU case, it will not be unique, but we will have also a new free parameter. Okay. So before going with the Darboux transformation, let us say something about the spectral analysis of a doubly infinite Jacobi matrix. Okay. More information can be found in this paper by Nikishin, or also in the paper by Mason and Repka. In this case, if we consider the eigenvalue equation, this eigenvalue equation, now we will have two linearly independent solutions or polynomial solutions given in terms of the initial condition. Depending on the initial condition, we will have two different families, but the free-term recurrence relation, it will be exactly the same as before. Okay, so these two solutions gives if we want to apply the spectral theorem, and now it will be a little bit different than before. But we can say that this P is self-adjoint in this space, in this Hilbert space, with this weighted sequence pi n, which is given by what is called the potential coefficients, but these are explicitly this sequence. So it's possible to see this extremely important property is that every canonical vector, if we design this somehow canonical vectors, then every canonical vector now we need two original E0 and E-1 in order to compute all the canonical vectors, okay, using the corresponding polynomials, the two families of polynomials, solving the eigenvalue equation, okay. This is different from the situation of the non-negative integers, where in the case of the non-negative integers, these factors here disappear. So in that case, we only have one cyclic vector, and we only have to apply the spectral theorem only once. So in this case, there are two cyclic vectors. So we need to apply the spectral theory not one but 4 times, okay, and this will be in here. Have to apply the spectral theorem 4 times and obtain 3 measures, because one of the measures will be by the symmetry. The measure psi 1 2 will be psi 2 1 by the symmetry of the self-adjointness of the operator. And we will have the following orthogonal relation between the polynomials and these measures, okay? So we can see that we have 3 measures, but we can write these 3 measures in a 2 times 2 matrix the following way. And in that case, we say that this is going to be the spectral matrix associated with the original matrix P, okay? Another way to write this orthogonal relation is the following, using the spectral matrix, is that the integral of vector qi2 multiplied by the psi of x, and then here we have to put qj1 and qj2, okay? We have a vectorial form of writing the same orthogonality relation, okay? Well, there is a very close relation with the theory of matrix valued orthogonal polynomials, and it's the following: is that if we write these matrix valued polynomials, where the positive indices are here, the negative indices are here, all these are polynomials, okay, and here the second family in the second column, then it is possible to see that this family of matrix valued polynomials satisfies this free-term recurrence relation where each of these blocks, each of these coefficients are 2 times 2 blocks, where here we can write the probabilities of the original matrix. All of these are just diagonal except for the first coefficient B0, which is not diagonal. Okay, but in this case, all the information is just the same as before, and the orthogonality is in terms of a usual matrix valued inner product, as we see here. Okay, and finally, the way of this relation with matrix valued orthogonal polynomials is just one way of folding the state space of the original P into a semi-infinite 2 times 2 block matrix, tridiagonal matrix, bold P. Okay. So in this situation, that means that the original set of non-negative integers is isomorphic to the following space. The non-negative integers, and now we have to consider what is called two phases, no? One going to infinity and the other to minus infinity. All right. Okay, so now let's go to the Darboux transformation. And as for the UL and LU cases, we have similar theorems. And the new thing about this is what is going to be the spectral matrix associated to the Darboux transformation. Okay, this Darboux transformation over here. And then again, we have to assume that the -1 moment is well defined, it's finite entry by entry. So in that case, we prove that the spectral matrix is going to be a conjugation by the Grünbaum matrix polynomial S0 given by exactly this expression, which is a polynomial of the Grünbaum. Here we see the x. And the measure in the middle is just Hieronymus transformation, no? Dividing the original spectral matrix by x, and then adding a Dirac delta at 0 with some magnitude that depends on the free parameter y0 and the -1 moment. Okay, this is one of the main results. So the same can be applied for the LU case, but now the free parameters are 0, and the discrete Darboux transformation again is similar. It's a conjugation of by the Grünbaum matrix polynomial, which is given here. This is depending on x, and this measure here is just again the Hieronymus transformation of the original one with some modifications, no? But basically it's just the same. Okay. Well, this is different for what happened in the case of non-negative integers, where in the case of LU factorization we have a Christoffel transformation, but here we have again some conjugation of a Hieronymus transformation. Okay. All right. So one example is following the case of the constant transition probabilities. In that case, if we assume this condition of the parameters A and C, we can compute explicitly the continued fractions H and H prime, and it's given by these values. In this case, also it's possible to see that the spectral matrix associated with the original matrix P is given by this expression, no? With defining this interval, depending on the probabilities A, B, and C. And here we have what is called the Darboux transformation associated with the UL factorization, which is the following matrix. We have this expression. We have the same as before, but we have now a second degree polynomial. Here is the second degree polynomial. Again, we have a Dirac delta with an m here. So one interesting thing about this case is the following. Let me erase this. Is the following is that when we choose the free parameter y0, either h prime or h, that means that this matrix will be 0, and also the matrix here M will also be 0. So in this case, we have that A and M will be 0. So A and M will be 0. And the rest of coefficients, no, we can see that we can arrange it in such a way that the spectral matrix is exactly the same as the original spectral matrix. Okay, this situation was not also possible in the case of non-negative integers, where the Darboux transformation, usually the spectral measure of the Darboux transformation is different, no? But in this case, there are some choices of the free parameter Y0 where the Darboux transformation gives it's invariant and gives you exactly the same measure as the original one. Okay. All right. So we will finish talk with different stochastic factorization, not necessarily UL or LU factorization, thinking about a probabilistic factorization. So in the previous cases, the UL or LU factorization means that the lower or upper bidiagonal matrix represents pure birth or pure death chains. Okay, so we now consider a different factorization, thinking in the factors are going to be a different chains. No? So one of the factors, we will try to find a reflecting birth-death chain from the state 0, and the other factor is going to be an absorbing birth-death chain to the state 0. Okay. Well, in that case, each of the factors PR and PA are going to be the following. This is PR, and here we have the diagrams of the states. The diagram corresponding to PR has to be a reflecting chain from the state 0, meaning that from here all the probabilities go in this direction or go in this direction. That means that we have to introduce, in order to connect these two chains, we have to introduce a new parameter alpha given in this entry. Okay. So the same for the absorbing birth-death chains. In the case of the absorbing birth-death chains, we have this chain, and then all the states converge or go to the state 0 with probability 1 eventually. Okay. So one important thing about these factorizations is the following remarks. The first thing is that this kind of reflecting absorbing factorization is not possible in the case of the non-negative integers, because in that case we have a regular UL factorization. We already say about this new parameter alpha, we have to consider in order to connect the chains. And one important remark is that the R, or the reflecting absorbing factorization, does not preserve the UL or LU structure, okay? Because as we see here, these are tridiagonal matrices, but these are not bidiagonal matrices, okay? So in that case, that doesn't preserve the UL or LU structure, but if we consider the folding trick, what we said before, the relation with the 2 times 2 block matrices, and we write in block matrices each of these factors, then the matrix PR is going to be an upper block 2 times 2 bidiagonal, and the matrix PA is going to be a 2 times 2 block lower bidiagonal matrix. Okay, so in that case, from the point of view of matrix valued situation, that preserves this UL structure. Okay, in that case, the main theorem here, we will have not one free parameter but 2 free parameters. That will be the new result, the parameter alpha and the parameter x0. And as before, in order to have a reflecting absorbing factorization, then this alpha has to be greater than h prime, and x0 has to be greater than the continuous fraction h, okay, as before. And another important thing now is that if we consider the Darboux transformation, now the Darboux transformation is not a birth-death chain, but now we have to add extra transitions between the state -1 and -1 and 1, as we see here in this diagram, okay? So this will not be a birth-death chain, but will be almost a birth-death chain if we consider these 2 factorizations, okay? That's the new thing about this. So we managed to compute the spectral matrix associated with the corresponding Darboux transformation, even if this is not a birthday chain. Okay, but we can use all the tools of the matrix valued theory to compute the corresponding spectral matrix. Okay, and in this case, now we will have that the spectral matrix associated with the Darboux transformation is going to be a regular conjugation by a S0, which is a constant matrix in the situation, and this psi u will be a Hieronymus transformation of the original spectral matrix. Okay, dividing by x and adding a Dirac delta, and also here we will have the corresponding magnitude will depend on two free parameters, okay, this situation. Okay, we can also consider the reversing, no, the absorbing reflecting, instead of reflecting absorbing, the absorbing reflecting factorization. But in that case, in order to have interesting results, we need to start with not a birthday chain, but an almost birthday chain with extra transitions between the states -1 and 1, okay? And in that case, also, we can identify the spectral measures, spectral matrix associated with the Darboux transformation. Okay. Okay, we finish with the same example as before, the random walk on the integers with constant transition probabilities. Again, we have the same value of continued fraction as long as we have to impose these conditions on the probabilities A and C. And this reflecting absorbing factorization will be possible in this situation. These two free parameters satisfy this condition. As before, the spectral matrix is of the original is this one here. And finally, well, we can compute the spectral matrix associated with the Darboux transformation, even if there is not a birthday chain on the integers. No? But using the result, we can compute the spectral measure, and it's given with these coefficients. No, will be a matrix of the degree 1 here and the same moment here, which can be written in terms of the parameters and the values of the continued fractions. Okay, so I think I will end up here, and I'm sorry I broke my promise of finishing before, but this is it. Okay, thank you.
Thank you.